All right, stat fans, let's get into some probability rules. So, the probability model is a description of some chance process. That's the key thing to take away from right there. This is a chance process that consists of two parts: a list of all the possible outcomes that could occur and the probability for each of those outcomes. The list of all possible outcomes is called the sample space. So right off to the side, you can see a little example of this just based on rolling a six-sided die. So you can see some die right there. But right here, we have the numbers 1 through 6 because that represents the sample space of all the possible outcomes of rolling a six-sided die. And then right below that, we have an event. And an event is any collection of outcomes from some chance process, that collection of outcomes. And the events of rolling a six-sided die all have the equal probability of 1/6 of a chance of occurring because you can only roll the number 1 once, the number 2 once, so on and so forth. Moving on, finding probabilities of equally likely outcomes. The formula of finding any probability, so the probability of event A would be in the denominator, the total number of outcomes that occur, and in the numerator, you would put the number of outcomes that you were looking for in event A. And an example of that is right over here on the right side. Let's say the probability of event A is getting a sum of 5 when you are rolling 2 fair dice. So there are 4 outcomes that have a sum of 5 when you are rolling 2 dice. Either you have 1 and 4 or 4 and 1. Something important to keep in mind. Notice the color of the dice. If the orange-ish dice is 1, then it could also be 4 in another iteration of getting a sum of 5. Likewise, you can have 2 and 3, but then the first die could be 3 and the second die could be 2. So there are 4 sums on a set of 2 fair dice that would give you a total sum of 5, but the denominator in this case is going to be the number 36. There is not an image that I prepared to have appear, but basically if you take all of the combinations of rolling 2 six-sided die, there are a total of 36 possible outcomes that could occur. So 4 of those outcomes would give you a sum of 5, and then the denominator would just be 36 because there are a total of 36 outcomes when you roll a six-sided die. But let's just go ahead and keep looking at some basic things that we're going to need in order to do some practice problems. So basic probability rules and laws. Number 1, if all outcomes in a sample space are equally likely, then the probability of A equals the, that image got way too small, but whatever, it's the same thing from the previous slide. The number of events of event A that you are looking for goes in the numerator, and the total number of outcomes would go in the denominator. Continuing on, number 2, the probability of any event is a number between 0 and 1. It's going to be a decimal number like 0.5 for 50%, and that would be a number between 0 and 1. Number 3, all possible outcomes together must have probabilities that add up to the number 1, because the number 1 is representing 100%, and that would be the total number of outcomes. You cannot have more than 100% of total probabilities of various outcomes because it's just not what it means. It's violating that rule. And then number 4, the probability that an event does not occur is solved by doing 1 minus the probability that the event does occur. You should absolutely put an extra star right by number 4. That is a type of question that's going to come up very often. It's going to ask you something like, what is the probability that something doesn't happen? You take the number 1 representing 100% and you subtract the probability that the event does occur. And what you're left with is the probability that it does not. Right below that, really quickly, the complement rule is just some notation that says the probability of the complement of A. That's what the little C means right there, complement. And the complement of A is saying you would be taking the probability of event A away from the number 1. The word complement means the event is not going to happen. Right here at the end of the sentence, the event that A does not occur. So if you notice the little c in the exponent, that means event A is not happening. And the way you can solve that is by doing 1 minus the probability that the event does happen. And we'll do a practice problem with that very shortly. Second bullet point, 2 events A and B are considered mutually exclusive if they have no outcomes in common and so can never occur together. That is, the probability of A and B equals 0. Throw the word intersection right next to that. That's what we're talking about. If 2 events are mutually exclusive, they have no intersection, they have no overlap if they are mutually exclusive events. So the probability of A and B occurring, which, by the way, the intersection symbol is an upside down U, and then the union symbol is a regular U, but those symbols will come up soon enough. So mutually exclusive events, lastly, that is where they have no intersection. Again, I should put the word no in right there. No intersection if 2 things are mutually exclusive. And then, lastly, the addition rule for mutually exclusive events. Very simple. If events A and B says that the probability of A or B happening is just the probability of A plus the probability of B, you simply actually add them together if they are mutually exclusive. You might know a previous or probability formula of the probability of A or B is going to equal the probability of A plus the probability of B minus the probability of A and B happening at the same time. And that is assuming that the intersection is not equal to 0. But if the events are mutually exclusive, if they have no intersection, then the formula would not include this last piece because the probability of the intersection happening would be 0. Because again, they're mutually exclusive. I'm saying those words a lot so it can hopefully associate when you hear it that mutually exclusive again means there is no intersection. What you see down here is just the algebraic notation of everything that was just said for the probability rules up here. So you can just see there is inequality notation that you can use, and then the variable S is used to describe the sample space. So the probability of S occurring would be equal to 1 because S stands for the entire sample space. And then once again, that formula where you have equally likely outcomes, it's just the fraction, the total number of outcomes that you are looking for in event A. On the previous slide, we talked about dice rolls, and there were 4 rolls that had a sum of 5, and then the denominator would be the total number of outcomes in a sample space, which for rolling 2 fair-sided die would be 36. And then the additive rule, you can see the formulas right there for mutually exclusive events. Mutually exclusive events, again, do not have an intersection. Oh, and then the complement rule, skip that part right there. The little c means the complement. All right, let's look at some practice problems. So, the perfect outfit. Mr. Jackson, which is Horizon's principal, has 3 shirts to choose from, white, orange, and purple, and 4 ties to choose from, purple, orange, white, and black. One morning after a storm, there is no electricity, and he chooses his outfit from the closet in the dark. In other words, he is randomly picking a shirt and tie. Give a probability model for the principal's random process. So when it says a probability model, it's just asking you to visualize what's going on here and show how the probabilities would essentially be calculated. There are many ways of doing it. Consider pausing the video and just making it as a list, but here we go. So there are shirts, so we can call this shirts, and then the shirts would be white, orange, and purple. So white, orange, and purple. All right, orange, and then white. Okay, and then, just to change colors here, we are now going to match his ties, and those ties are going to be like this. So there is a white tie, a orange, a black, and a purple tie. So the white tie, the white shirt can go with a white tie, an orange tie, a purple tie, and a black tie. That was right. Yeah, black tie. And then the orange shirt can also go with a white tie, an orange tie, a purple tie, and a black tie. And then the purple tie can lastly do the exact same thing, going with a white tie, orange, purple, and black. Now, you could take the time to just write the rest of the words there. I'm just not going to do that right now because I'm making this video on the fly. But what you can basically notice is each of the 4 ties can get paired with one of the 3 shirts, meaning the 3 shirts multiplied by the 4 types of ties gives you a total sample space of 12. So we're just trying to show a model to describe the random process of choosing any one of these combinations. You would show the work right here and probably want to write out the rest of the words instead of just putting the first letters down of the colors of the ties. But what you would then describe is each outcome has a 1/12 chance of occurring. So, Part B, define event A as the outfit that has matching color shirt and tie, and that is event A. So we're trying to find the probability of event A occurring. So we need all of the combinations where it is a matching shirt and tie. So we have a white tie and a white shirt, orange tie, orange shirt, and purple tie and purple shirt. So it looks like there was 1, 2, 3 combinations out of the 12 options in the sample space. So that gives a 20, or we'll first write down 1/4, or a 25% chance of getting a matching color shirt and tie. All right, moving on. Wing night. Buffalo Wild Wings ran a promotion called Blazin' Bonus, in which every $25 gift card purchased also received a bonus gift card for $5, $15, $25, or $100. According to the company, here are the probabilities for each bonus gift card. Explain why this is a valid probability model. Well, your probability models are supposed to add up to a particular number. our probability models should add up to 1.00, representing 100%. And if you add up all four of these numbers, just do it on a calculator, you would get 1.00, meaning this is a valid probability model. And in addition to that, all of the decimal values that you see here are falling between the numbers 0 and 1. So again, this is just giving us something that represents a true probability model. And plus, it is quite reasonable that, for example, the $100 gift card would have a very low probability of occurring, being 0.002, 0.2% chance that you would get the $100 gift card. So all of it makes sense because everything adds up, or we should call it like this: all probabilities add up to 1.00. And maybe just show some plus signs right there and why that's happening. Part B, find the probability that you don't get a $5 bonus card. So the probability that you don't get something means you are getting the complement. So the $5 gift card would get the little C that you would be getting there. And that means you would do 1 minus the probability of getting a $5 bonus card. You're not getting it. So you would care about the probabilities of getting everything that's not the $5 gift card. You could add up those three values right there, but you don't have to. You can just use the formula 1 minus the probability of getting a $5 gift card, which would be 1 minus 0.890. And that's going to leave us with 0.11, or an 11% chance to not get a $5 gift card. And part C, what is the probability that you get $25 gift card or the $100 bonus gift card? So an or problem, and these are events that are mutually exclusive, so there's no intersection here. The probability of getting that $25 gift card is 0.010. You can see that right there. And then you would simply add the probability of getting the $100 gift card, which is 0.002, and that is going to give you 0.0012. And that would be 1.2%. All right, moving on. Let's do another one. So the general addition rule in mathematics and probability, A or B, means it could be A or B, or both A and B happening at the same time. If A and B are any two events resulting from some chance process, the general addition rule says that the probability of A or B is equal to the probability of A plus the probability of B minus the intersection of A and B, which was referenced on a previous slide. The probability of A and B, that events A and B both occur at the same time, is called a joint probability, which you might have heard from a frequency table if you heard the term joint relative frequency before. This is essentially the same idea, it's just probability, so you're going to be seeing more percentages. If the disjoint probability is equal to 0, the events are considered, or if the joint probability is equal to 0, then the events are considered disjoint, mutually exclusive. They have no intersection. Let's take a look at another example. Subject preference and gender, two-way tables and probability. Do males and females have a different preference for math or English classes? The two-way table summarizes data about gender and subject preference for a class of 25 AP students. That number will probably be important. Suppose we choose a student from the class at random, define event A as getting a male student and event B as getting a student who prefers math class. All right, so part A, find the probability of event A. Event A is getting a male student. We can see male students right there, and there are 10 of them. Let me just make that 10 a little bit clear. There we go. 10 of them out of the 25 total. So we have 10 over 25, which if we divide both of those by 5, then we will have 2/5, which is a 40% chance of getting a male student. Number 2, find the probability of A and B, and then interpret this value in the context. So that is going to be the intersection, also denoted by the upside down U. Now, just using the formula first, we would take the probability of A, which we just got to be, there were 10 out of 25. And then, or the probability of event A, there were 10 people. We don't need to do the fraction part yet. And then the probability of event B, which is going to be getting a student who prefers math class. So there is math class, and there is 20 right there in that grouping. And then we will subtract the probability of A and B happening at the same time. And that probability is where the two row and column combinations intersect. There were 8 male students who were also taking math. And in the 10 that I'm underlining in purple, those 10 people have that 8 added in there. And the 20 people that are over here on the right also have those same 8 overlapping male math students being counted twice. So that is why you have to subtract off the extra duplicate intersection probability at the end of the formula. So we're going to minus 8 right there. And this idea will come up again and again if you don't fully get it, and I'll even tell you another way to do it in just a second. But the denominator still going to be the total number of outcomes. 10 plus 20 is 30, minus 8 is 22. So we have 22 over 25 is going to be our probability. And that is going to give us 88%. And in the context of the problem, there is an 88% chance that a student chosen at random likes math or is male. Messy handwriting, but so be it. Part C. Find the probability of A or B. Oh, and in just doing this really quickly, I realize I just reversed these two questions right here. And what I just answered in purple would be the answer for the or events. Oh, right there. Oh, well, whatever. We can quickly fix that. We're not going to adjust that right now. It's Halloween. I just want to get this video up so that we can work from it. I will just leave it there. You're listening. We will just clarify by saying what is in purple. I just answered the or problem, which is part C. And I just went on a streak of talking about the intersection problem with kind of getting ahead of myself. So just to clarify, let me switch to black. So the probability of A and B, where you have both the preferred subject of math intersecting with gender, would be the number 8 you see right there. So that would be 8 out of 25. Which is going to be equal to 32% chance. So that is the answer to part B. There is a 32% chance that a student chosen at random likes both math and is male. That's the answer to part B. And the answer to part C is what I wrote in purple, where we had to add up the two probabilities and subtract the intersection. Things got a little sloppy, but whatever. Hopefully you're listening, and this video will probably be redone in the future anyway, whatever. All right, number 7, couple more. Where are the best tacos? A survey of all students at a large high school revealed that in the last month, 38% of them had dined at Taco Bell, 16% dined at Chipotle, and 9 had dined at both. Suppose we select a student at random. What is the probability that the student has dined in Taco Bell or Chipotle in the last month? Now, with a Venn diagram, this has been talked about in class. Hopefully you have a little bit of familiarity with it. Basically, the two circles represent the two dining places that we are looking at. We have Taco Bell, which we will put TB, and we will put a CH for Chipotle right there. And what you see in the middle is the probability of both of those events occurring. And the way you handle a problem like this is you start by placing the joint probability, the intersection, the 9% of people who had dined in both of these locations. And then you understand the following. Taco Bell, 38% of them, this entire circle of Taco Bell has to be 38% of the data, but you already accounted for 9% of the data in the intersection. So that means you have to do 38% minus 9% to get the answer for the amount of students who only dined at Taco Bell and not also Chipotle. So 38 minus 9 is going to give you 29% of the data. And with the exact same logic, you would deal with the Chipotle people. There were 16% who dined at Chipotle, but this 16 represents this entire circle, including the both people that you already accounted for, which was the 9%. So we will again have to subtract 9, and that is going to give us 7% of the data of only people who went to Chipotle. And then lastly, we are asked the question, what is the probability that they have dined at Taco Bell or Chipotle? So that would mean you would be taking the probability of event A, which was Taco Bell. You would be adding the probability of Chipotle, which was 16, and then subtracting the overlap of both of those places being dined in. And that is going to give you 45%. And also, you can get that answer by just adding up the probabilities that you see in the Venn diagram. Either 29% only had Taco Bell, 9% had both, 7% had Chipotle, so that would account for everybody. Oh, and then we need to put the complement of Taco Bell and Chipotle, which is where you would do 1 minus the probability of having any one of these places. And there would be a 45% chance of that happening. So that means the complement of the people who didn't dine in any of these establishments would be 1 minus 45%, and that would be 55%. All right, one more question. The Venn diagram situation will now be explained a little bit more right here. We did talk about it in class, but basically a Venn diagram consists of one or more circles surrounded by a rectangle. Each circle represents an event. The region inside the rectangle represents the sample space of the chance process. So right over here, you can just see a basic idea of owning a cat or a dog. There are 3 people in the intersection, meaning those 3 people own both a dog and a cat. And then we can say event A is owning a dog and event B is owning a cat. And 5 people own only a dog, but a total of 8 people own a dog or a cat, or a dog, or they could also include the people who own a cat. We saw this on the previous slide. It's just an example. Let's just get to these little symbols right here. Once again, in a Venn diagram, when you have the sort of exponent position of the small c, that is talking about the complement, the probability that the event does not occur. So all of the outcomes that are not in event A. And then you are seeing in the second image the intersection symbol, which is denoted by the upside down U. The intersection is the set where all outcomes in both events A and B take place. That is the intersection, and that would be what I'm going to darken in red right there. And then we have the union symbol, so that is a normal U. The union is the events A and B, and that is the set of all outcomes in either events A or events B happening together. So that would be the union of A and B. And it also includes the intersection because, again, it's all the outcomes, the union symbol. You are joining together all of the possible outcomes that happen in this sample space. So that would be event A, event B, and events A and B happening at the same time, which is kind of the opposite of the intersection where you're, or well, sort of just a different concept from the intersection, which is only the overlapping region. All right, one more. Apple Music or Spotify. According to a recent report, Apple Music and Spotify are the most used streaming apps. A group of AP Statistics students surveyed all the seniors in their school and found that 68% use Apple Music, 38% use Spotify, and 24% use both. So suppose we select a senior at random. Make a Venn diagram to display the sample space of this random process with events A using Apple Music and event S using Spotify. So once again, maybe pause the video, try to do this one on your own. We have event A for Apple Music and S for Spotify. 24% uses both, so that's going to go in the middle for the intersection. And since the entire circle for Spotify is supposed to be 38%, but we already accounted for 24 of them in the intersection, we are just going to subtract, and that is going to give us 14%. And then for the same logic, we do that with Apple Music. The entire circle is representing the 68% of people that use Apple Music, but we are going to take away the 24% that are using both because we don't want that overlap to be counted twice, and that is going to bring us down to 44% of people who only use Apple Music. And we will also include the complement, which would be 1 minus. If we add up 44 plus 24, that's going to get us back to 68, and then we're going to add 14 to 68, and that is 82%. So the probability that somebody does not use any of these music platforms would be 1 minus 82%, which is 18%. So that would be located in the complement. Oh, let's get that 82 out of there. Part B, I actually just took care of that as I was just talking. The probability that a person uses neither Apple Music nor Spotify, I was just kind of riffing, and I answered that question anyway. You would add up the individual probabilities of people listening to Apple Music or Spotify or both, and you would subtract that number from 1, which would be the total number of, or the total probability of all the events taking place. Sorry, this video went a little long, but just doing it on the spot, and that's just how it goes sometimes. Hopefully everything makes sense enough where you can complete your homework, and I will see you guys pretty soon. All right, bye.